Z naught, that's the characteristic impedance of this guy, right here. I should say this is Z naught. Or characteristic impedance of the transmission line, times ZL, that's this, plus J Z naught times the tangent of beta L over Z naught plus J Z L times tangent of beta L. Y'all with me? I just put down the front. Then you should know this equation. I'll give it to you. And make sure you know how to use it. So for this, the length of this line is lambda over 4. Everybody follow? That is an absolute must for this. And this matching only works at one frequency. This is real important. So if you look at this, that means beta times L, that's the argument of these tangents. Well, beta is 2 pi over lambda, and L is lambda over 4. So that means this is pi over 2. Y'all follow me? Everybody with me? Now, what is if you think about the tangent function, what does it do from 0 to pi over 2, or 90 degrees? Well, it starts at 0, then at what? And asymptotically, I'm not drawing this right, but it asymptotically goes to infinity at pi over 2. Do you all agree? It's discontinuous. That comes in from minus infinity down here. Now, if you look at this, I've got to get it different. This is just not good. This has been erasing for years. If you look at this, these two are becoming extremely large. Do y'all follow me? So large that we can ignore this, and we can ignore the J's, and these two cancel. So we find out it's simply Z naught squared over ZL is equal to Zn. That's all it is. With me on that, class? If it's a quarter wavelength long, and you want to know the value of Z naught that would match it, right? That's the characteristic impedance. Y'all follow me on this, class? You can take a look at this, and it becomes Z naught is equal to the square root of Zn times ZL. This would be the characteristic impedance of this transmission line right here. Now he tells us it's coming from a transmission line that's got 50 ohms. Itself is 170. That means the actual characteristic impedance of this, the transmission line right there, would have to be the square root of 170 times 50. And I don't know what that is, but what is that?
It's 92.
80? Huh?
92.
92? 92 ohms. Now, you can't do this with coax cables. You hear me? Coax cables, they come in very discrete values like 75 ohms, 50 ohms. They don't have any ohms. Here's what they do when they make these things. And this is further on down the line when you get to microstrips. Usually what they do is this. A microstrip is really a piece of copper. It's a copper board. And it's going to have some dielectric. But above that dielectric, they're going to have, so there's some dielectric here. But what they'll do is, they'll have over that dielectric, they're going to have, actually, do it this way. That's a dielectric, so this has some very epsilon relative. They'll get a line, a very thin piece of copper here. Now, we can get into this later. That has a width. This has a thickness T. The ratio of width to thickness determines the characteristic impedance, and also it's based on epsilon relative, but that's further down the line. So you can customize, you can make, and basically this thing is going to be long. It's going to be greater than lambda over 10. The length there, it's greater than lambda over 10. But they'll make a piece of that, and it will be customized, so it'll have exactly the characteristic impedance for matching. Got me on this, class? But it works only at one frequency. Those kind of applications have to do when you have, you know what lithography is, everybody? You know, when you make, VLSI uses, all the places do it. And when we say we pattern just FR4 that has copper on it, well, we can make the connections between any 2 points just with this to do matching if it's a strictly real load. Now you can't do this if it's they got a real and imaginary component to the load, only for real loads. Do you follow me? That's real important, appreciate that. But it does work. This is called a quarter wave matching transformer. It's used a lot if you're matching like antennas at a given frequency and it's coming right off a power amp on a board or something like that. You can do that. You don't need to do matching with a stub. Go ahead.
Additionally, it asks for the through line lengths and the stub length for a shunted shunt stub.
Well, it has to give a frequency.
It does not.
Then they want it in okay, they want this in quarter, they want it in terms of wavelengths.
I guess.
All right, so now we'll do that over here. How about we do it right here? You all see how the quarter wave works, right?
Yeah.
So now we match 170 ohms to 50 ohms, right?
Mm-hmm.
And now this is a standard transmission or shunt. You want to do it with parallel or series? Does it say?
It says shorted shunt.
All right, shunt indicates parallel.
Yeah.
And it's shorted? Okay. So here's what we're doing here. We have a load. We have a transmission line. And now what we're going to do is use a shorted parallel shunt stub. This would be the stub link. And this is going to be the through line. All right. We're going to calculate those. This Z naught is 150,
Yes.
right? And ZL is 170, right? Correct, class?
Yeah.
Does he want minimal distance or what?
I didn't say minimal.
We'll just do it any which way we can. All right, follow me. First step is always what? We're doing impedance matching with stubs.
Normalize.
Yeah.
What?
Normalize.
Normalize. What do you get for this? ZL is 170 over 50. What is that?
It's 3.4.
Forget. Don't worry about that. Well, okay, go ahead. What is it?
3.4.
3.4 and 1 over that. YL is,
0.29.
what is it?
0.29. Yeah.
Okay, so, you need a Smith chart. Let's go here. This is an interesting problem in a way. Because almost all of the matching was done with a real and imaginary component to the impedance. But strictly real, if you can, probably just go with that quarter wave. Okay, so now, let's see. Here's my Smith chart. That's exactly ours. Y'all with me on this, class? So ZL is 3.4. It's strict real, right? All right, so, and plus J0, right? Where's J0?
It's just on the wall.
Right here. Y'all follow me? That's J0 right here. Got me on that? So 170, I'm going to guess, is about here. Or not 170, sorry, 3.4. My bad. It's about 3.4, something right in there. Can you follow that point? I mean, got me on that?
Yeah.
Now, what do we need to do to match? Well, we have to go to the, we're in parallel, that's impedance, we need to go to admittance, right? 1 over that. Is it closer this way or what?
Yeah, it's a little further that way.
How about, we'll put it right there, we'll call that 3.4, okay?
Sure.
Now we go to, we can draw a circle around, might as well just take a circle and go around here. And the conjugate point here is YL, 1 over, to normalize that, follow me? That's that point 29. All right, we're at 0, correct, class? That's where we start. We move how far? We can move to 2 spots, right? If we're moving wavelengths towards generator, we can move here, or we can move here, right? He doesn't say which one he wants in terms of, he doesn't tell us what is the shortest distance. This would be the shortest through line. Do y'all agree with that, class? So you take your straight edge and draw it right through there. Somebody tell me what this is, wavelengths towards generator.
0.170.
All right, now you'll realize we started at 0 wavelengths towards generator here. So that's the length of the through line. Everybody agree with that? So it's 0. 170 lambda. Now for the stub, I take a look at this, and I have an imaginary part of J something. What is that?
1 point. Yeah.
1.3? You with me, class? All right, now we take a look at the stub. It's shorted. So the stub is shorted, and I always do this. It's got we're going to assume it's characteristic impedance Z0. It doesn't have to be. We can account for that too, but I'm not going to do that now. I want to just focus on the basics. Almost always, the stub and the main line have the same characteristic impedance. Almost always. If not, you have to adjust it. Okay, now that's Z0. That's a short. What is the short circuit value for normalized impedance? 0, and YL for that is? Infinity. So we come in here. You agree? We're right on the rim, correct? And we have to go until we hit what? That's plus J1.3. We have to go until we hit about here, minus J1.3, correct? Can you all see that on your, now let's take your straight edge and go right through there, through that point, and tell me what the marker is wavelengths towards generator.
That's 0.354.
0.354?
Yes.
So that means this D stub is equal to 0.354 minus 0.25 wavelengths, and what's that? That's
0.104.
0.04, isn't it?
It'd be
Oh, I'm sorry. My bad. I'm sorry. It's 0.104, just over a tenth of a wavelength. Do you agree with that? That's a solution. That does the job. Now, if we went to here, this point, this is going to be 1 minus J, or yeah, 1 minus J 1.3, right? And how far would we have to go then with this? I mean, if we went all the way around to here, we have 1 minus J 1.3, right?
Mm-hmm.
So for the stub, we have to go to up here to plus J 1.3. Y'all follow me on that? But that's the technique. Any questions? Try to make it as easy and clear as possible. That's an odd one because the loads, almost all the loads he gives you have a real and imaginary part. Almost. This one. Another question?
Can we do the second part of? I guess we can do all of 242.
Yeah. Which one is that?
It was the last one you assigned. It
Okay.
was here, I can read it.
Hold on. Let me erase this first. Yeah. You can read it. Does anybody know what the weather is today and tomorrow?
I think it's supposed to be sunny all day today.
Is it really?
Supposed to.
Is there a baseball? There is a baseball game, right?
Yeah, today.
They were blocking off the roads because I guess it's the tournament or the regional stuff. And so I had to go home and walk my dog. My wife's out of town. And I was driving home and they were already blocking up the street so you can't drive near the baseball stadium.
Tomorrow's supposed to be sunny too.
Good. Okay, this is 2.42, did you say?
Yeah, this is the one where he gives you like a load to match, blah blah blah, and then it says now suppose the load turns out to be something different.
Let's do the first part.
So it says design an open-ended shunt stub matching network to match a Z
Well,
load.
an open stuff, shunt stuff, right?
Yeah, open
Shunt.
shunt. Open shunt, yeah.
Okay, so let me just draw that first. Here's the load. We're going to have, I'll just call it D through. Here we're connecting, and this is an open, so, and this is the stub length. Call this D stub. And all Z not characteristic impedance, right?
It
50
says 50 ohm, and then the load is 70 plus J110.
Okay.
It says choose a solution that minimizes the length of the through line. That's just part one.
Okay, so what do we do?
Normalize.
Well, what is that going to be? 70 plus J110 over 50, right, is
1.4
plus J2.2.
Yeah.
Okay, and here's my handy dandy Smith chart. It's the smaller one. So 1.4 plus J 2.2. J 2.2 is about here, I think. You can correct me. And J 1.4 is a circle about here, just inside here. And so if you look at where these trajectories hit, it's about here. This is ZL. Do you agree with that, class?
Yeah.
Roughly.
Yeah.
Now, we're matching it in parallel or shunt, so we go to the admittance domain. Everybody follow me on that? So I'm going to draw a triangle. It's the circle of that radius, which is drawn too well. Now I go right through that circle to here. This is the same distance, and I get YL, which is 1 over ZL. And what is that?
0.205 minus J 0.323.
205 minus J, what?
0.323.
323? And you're going to have to draw a line right through there and give me the wavelengths towards generator mile marker. I call it a mile marker.
0.45.
Yeah.
0.45 lambda. Okay. Now it says the ones that minimizes the distance of the through line.
Yeah.
Okay. That's this point, isn't it? I mean, right here. Right. If we start here and we move, this is the first point we can hit on the one circle. That would be the shortest distance, right?
I have a question conceptually. Do you always move this way because you're going towards the generator?
It's the only way you can.
That's
If
the
you
only way
look,
you can
if you
go.
look on there, it says WTG. It's wavelengths towards generator. So if you're at the load, the only place you can go is towards the generator.
Okay. So when it says, oh, you got it.
No, you were finishing your question. I had
Okay.
that question afterwards.
So basically, if it always says minimize, then it's gonna be like the top.
Shortest
most-
distance.
If it says shortest distance, it's gonna be the top most of the
Well,
time.
you don't
or
know.
through
It could
line?
be in here, right? If it's in here, this is the shortest.
That's the shortest distance of D, not the L stub, right?
Yeah, right.
Okay.
Yeah, I was about to ask if we wanted to find the shortest distance of L stub, what would we?
All right, well, then you have to look at the stub. The stub is open, right?
Yeah.
All right, if it's open, what's the impedance of an open circuit?
Infinite.
And what is the admittance of an open circuit?
0, 0.
So that means for that stub, we're starting here, right?
Mm-hmm.
Now, all the values on this side are positive J. If we want to minimize the distance or the length of the stub, just hear me now, you want to make sure it's got to be a plus J term, right?
So you match it with the minus J, so we set the
That's
circle
right. Then you would go from here to there, so it's got a minus J value from the load to get
Okay.
rid of.
Okay.
That's
So
if the
that-
rationale's clear, it should be.
So they kind of like inverses of each other, like to make one longer, one's like shorter.
like
I don't know.
that
I don't know
word.
if inverse is the right word, but like.
Well, look, now it depends on the type of stuff.
Okay.
Open versus short require two different things, and you got to think it through. This
Yeah.
isn't open. If it was a short, it's
Oh
totally
yeah,
different.
that'd be
If it's a short, you start here, right?
And then you get yeah.
All right, now it's important you guys
Gotcha.
understand. You think these through. Don't react. Oh, that's how I did it in the book. I remember. Just you got to think it through at every level. And I see too many students just kind of react. I saw that in the quiz and in random. That some people just I think that's. They put down a bunch of stuff that they didn't really think about. They just reacted. Okay, so the distance of the through line. We go to there, right?
Yeah.
All right. So what is, if you go from here and shoot a line right through there, what's the wavelengths towards generator?
Oh.
0.182, correct, class?
Mm-hmm.
About. So what's the total length of the through line right here? It's going to be where we landed is 0.18. Where we came from is 0.45. Is that right? 0.45. Now it's going to be negative, so you got to add 0.5 to it. And what's that value?
0.232.
All right, 0.232 lambda, just shy. No, it's actually over a half or quarter. It's over a quarter wavelength.
No, that's right. Isn't it right under?
Oh, point.
right
I'm
under.
sorry, it's just under. My bad. I can't think or see. Anyway, we get that. We've got that line. Now we need this stub length. So over here, what's the value? It's 1 plus J what? You gotta go this way. J. Anybody?
I got 1.8.
1.8. Anybody would confirm that?
Oh, let me check.
Huh? Just look.
Yeah, I got like 1.8, 1.9. Remember that
You
area?
guys good with that? Okay, I'll go with 1.8. So that roughly, okay? Now, that means what? We're back to this thing. We got to get rid of the J 1.8,
So
right?
we need minus J.
That's right. So this is an open, right? Infinite. We go in the Y domain because it's in parallel. It's 0. We start here, right here. And we go until we hit,
Minus J 1.8.
and that's minus J 1.8. I'm going to guess is if that's 1, maybe about here. So it's minus J 1.8 here, and you got to shoot a line right through there, right? And what's the mile marker on that? 0.321? 3.3. Is that right? And that means that would be the total distance right here for this stuff. All right, now, second part. What does he say?
Okay, so he said, now suppose the load turns out to be ZL equals 40 plus J100.
Okay, stop right there. We've already got the links. With me?
Yeah.
So now we got 40 plus J100.
Yeah.
Okay.
And it says, determine the reflection coefficient seen looking into the matching network.
All right, basically the reflection coefficient on this side.
Yeah.
All right, now we're going to do this problem. Now it doesn't match, but we've got to still figure it out going through the same reasoning process, okay? So maybe I need another switch right here. I'm going to do it right here. Leave that one. And first, our load is 40 plus J100 divided by 50, right? So that means ZL is 40 plus J100, 100, right?
Yeah.
Divided by 50, right? And that's going to be 8.8 plus J2, correct, class?
Yep.
All right, so 2 is roughly here. And J2 would be about here, I think. Isn't that about J2, class? So this is going to be where ZL is. Okay. Now, we're going to do this in the admittance domain. Y'all with me? Okay. Now, from there, come down. That's the center. This is that reflection coefficient at the low magnitude. Now, draw a circle of that radius. I think his solutions are right on this one, but I don't really remember. And this is going to be y of the load, right? Correct, class?
Yeah.
Just 1 over z of the load. And, you've got the numbers. So you draw a line right out there and tell me what the wavelengths towards generator is there.
I got 0.434.
0.434. Is that right, class?
Yeah.
All right. Now, we know the length of the line from before. The through line is 0.232, correct? So what we're going to do is add that to this. Follow me?
Okay.
And then what do we have to do? Subtract off a half wavelength because it's greater than a half wavelength. Y'all with me? We're going to keep adding, and we're going to go. And we're going to find the distance that we actually end up at, wherever it is. This distance, I'll just call it, let me call it blank wavelengths towards generator. The point we want is going to be 0.434 plus 0.232. 0.232. That's greater than a half wavelength, so we subtract 0.5 from it. And tell me what you get.
0.166.
0.166. So, that is about here, is that right?
Yeah, more or less.
So this is 0.1669, something. I'm just trying to estimate this. So you shoot a line through there, right? Okay. Now, we started here. We're going to move, right, until we're at this point. Now, this is not on the one side. I don't know what it is, but you're going to get a point right there. Give me the value of y there. this, I'll call it yn, and that's the value of y looking here.
I want to say it's 0.6 plus J 1.7.
So this is 0.6 plus j
1.7.
1.7.
Yeah,
Is that about right, guys?
I think so. I didn't get this far in this problem, so.
I mean, he has the answer,
I
right?
can check. What is this?
Doesn't? Did you
Yeah,
do this
yeah.
one?
Oh, no, I can do part B. I did part A.
Well, part B is pretty good, because this is the kind of question that probes you to see if you really understand. You with me, class? All right, now, it's 0.6 plus J 1.7, right? What did we add here? What was the value?
1, 2,
The value of
Oh.
impedance. It was what, normalized minus J 1.8?
Yeah.
Is that right, class?
Mm-hmm.
Go ahead. Y'all follow me?
Yeah.
This is admittance. That's admittance, right?
Yeah.
We add them together. So that means at this juncture right here, the sum of this y value and this y value, or the y value here that the z naught would see normalized, the y in would be equal to 0.6 plus j 1.7. And it's going to be minus j 1.8, right? Isn't that right, guys? So that's 0.6 minus j 0.1, if I did the math right. Do you all agree with this? Now that's admittance, correct?
Yeah.
I'm going to take this back to the impedance domain so you see this. That's normalized admittance. Normalized impedance, the Zn, this is normalized though, would be 1 over that. So 1 over y. Can you tell me what that is? You may not do it this way, but I'm going to do it this way. What is it again?
Well, 1 over that is going to be 1.62 plus J
1.62 plus j1?
0.27.
27. Anybody confirm that? I believe you. But I like to get a second opinion. Anytime, here's one tip I'll give you. Anytime you're doing calculations where it's very important to get the right answer, like money on the line and stuff like this, or do the calculations twice. I mean, I always do that. I've learned the best solution to preventing, it's better to not make a mistake than make one and then have to work backwards in the design. Okay, so that's the value of the normalized admittance, right? I mean impedance, pardon me, right? Now I want you to just watch this. So, and I'll do it here. We can do this a lot of different ways. First, I'm going to do it from the standpoint of just the basic equation. He wants the reflection coefficient. Is that it? Is that it?
Yep.
Okay. Well, you know the reflection coefficient, and this would be at the effective load because that's the combination of where the juncture is between the load and the stub. I mean, load in the through line and the stub. So this is an effective load, but it's normally ZL minus Z naught over ZL plus Z naught. You all follow me?
Yeah.
Now, if you divide top and bottom by Z naught, you get ZL minus 1 over ZL plus 1, right? You agree? So, I mean, do you all follow me? I'm just showing. So you can literally say the reflection coefficient, this is one way, the effective reflection coefficient is just going to be that. And I mean, you can do this quicker than I can. Can you just take this as ZL and put it in that equation and get it? I'll show you a second way to go.
Which ZL? The one from over there?
This is, I'm calling it, it's
Yeah,
really
that guy. Yeah, okay. I was making sure I was talking about the same
roll
number.
it. Wait. Where did I? Yeah. That's y and that's this right here. I'm calling this the normalized ZL. I'm just using it effectively that. Y'all follow me? What you think? Broke or
No,
something?
I'm just, I don't know.
All right. Y'all with me, class? All right. So what do you get for this?
I got 0.245.
Hold it. 0.245 at an angle of
Oh, no, I have it in, sorry, never mind.
what?
I have it in a rectangular.
No, I need this,
Yeah.
it's gotta be in polar, magnitude and angle. If you got a rectangle, you can go
Yeah,
from
that's what I'm doing.
rect to polar, I think, fairly easily.
I have not used that in a while in this calculator though. So I don't.
Or you'll be using a lot in engineering, actually.
I can like compute it like with the rectangular form. It'll take a minute.
Polar is what I need.
Yeah, I know, but I can compute the polar form
Okay,
because I can't. Unless someone else can do it faster.
did you got?
No,
Because that would be
What do you
helpful.
I got 0.7 e to the 31.92.
What, say again?
0.70 e to the 31.92.
The what?
31.92. Like, I may have messed up.
Something's really
Yeah,
off.
Could we look on the Smith chart to get this instead?
Yeah,
to
we're
make it
gonna,
easier?
but I want this for
Okay.
calculus. We're gonna, trust me. Just give me,
For my magnitude,
tell me what it is, please.
I'll get in a second.
You should be able to do this fairly efficiently. You can do it in rectangle and just go rect to polar, right?
I don't remember where it is.
you have to do the there's like a symbol.
You just
Well,
do.
we have different calculators.
What did you get for rectangular?
0.24, wait. Yeah, 0.24514 and 0.0778.
For what?
That's rectangular.
0.77.
Yes, 0.0778.
Alright.
What'd you
Okay.
get?
The magnitude's 0.255.
0.255.
I got about that.
What angle?
Hold on, let me get the
What?
real quick. I got, is it tangent inverse?
Okay,
This usually isn't far where it holds. It's usually these long Z in calculations with tangents and fade out.
Okay, I got 0.257 times e to the 0.307. I'm in radians. Do you want it in degrees?
Yeah,
Okay. Hold on.
just
Multiply by
180 over pi. It's 57 point something.
Okay, 17.6 degrees.
Anybody?
I got
else?
that as well.
17.6 degrees? Wow. That's one way to do it, right? Now, on a Smith chart, can we plot this point? I just want to do this one, okay? Can we plot it? Remember, it's Z, not Y. Where is that about? So we got 1.62 is inside this circle. I'm just going to erase this stuff and show you what I'm talking about. So if we go 1.62 plus J 0.27, I'm going to say it's about here. Take a look. 1.62 plus J 0.27. Can y'all find that in your Smith chart?
yeah, it's close enough.
Y'all with me? You good with it? All right, now, take your, whatever, straight edge, draw a line to there. This is going to be the magnitude of the reflection coefficient. This is the angle. If you read on your, I guess I didn't draw this very well, but it's going to be that angle. Can you all see it there, class? The magnitude here, you can go down to the bottom of your Smith chart, and there's something called, I think, REF, E/I REF or something like that.
Yeah.
All right, now just take it, measure this distance, go down there and measure it. And that's probably not drawn real well, but you get the idea. What do you get for your reflection coefficient down there? About.
I feel like 17.6.
You did
Oh,
the
that's
wrong-
the
really
angle. That's the angle. Sorry.
Right, that's
Oh, the
the,
reflection coefficient?
Yeah.
Yeah.
Oh, isn't that just the...
Draw the straight edge down.
Oh, it's
you
just
can do
down
it
this
that way. Yeah.
Or you can.
Don't
You
you just
can
get like
just-
the length or something?
Yeah, look, take your, you got a good
Hold on,
compass,
I'll get
right?
a second.
Take this distance right here.
here to here.
Just take it down the bottom.
I got 0.26 maybe.
Yeah.
There you go.
Okay, you follow me? That's the way you would do it if you just wanted to use the Smith chart. But I wanted to show you both of these. Okay, that's a good problem, by the way. You know, there's a lot of times what happens on exams is you get a whole bunch of problems that really expose you to the theory where you're working. Then the prof will give you, or in the real world, you run into a problem where you've got all the information in the theory down, but it's different like this one. So you have to think it through, make sure. If you understand the theory, this is an easy problem. But if you're a little uncertain about the theory, then it exposes your weaknesses. That's what this one's good for. Another question?
I have a 2.39.
Okay. Let me erase this.
I just have a question about it conceptually, but like if you do it, I'll ask the question.
Right here.
When's the last time it rained around here? It seems like it's been quite a
It's
while.
been like a week. It's actually not supposed to rain for the next week or so.
My yard is starting to feel it. I have to turn on this one. Okay. So, 2.39? Go ahead.
So this is an open shunt.
Okay, so we got transmission line load, right? Characteristic impedance Z naught. And then we got a shunt and it's got an open circuit, right?
Yep.
What's the length, or tell me the information.
Tell you the what? The ZL is 200 plus J160. And 160.
60.
And ZL is 100.
This is Z
Or,
naught.
I'm sorry, Z naught. Whoops.
Z naught is, my bad, 100, right? Go ahead.
Minimize the length of the shorted stub.
Okay, now, we just basically did this kind of thing, right?
Yeah.
Okay, so, here's the yield circuit chart. This is, okay. And first thing is ZL, right? ZL is simply going to be 2 plus what? J1.6. And so 2 is here, roughly, and 1.6, if this is J1, this is about J1.6 here. So something like that. This is going to be ZL, right? That's 0.1. Do this for me on your Smith charts for quiz. Do put like 0.1 so I know the progression. Sometimes on a Smith chart, I'll see all sorts of stuff and I don't know what he did. I don't know where he started, where he ended up.
You don't see that on like tests and stuff?
Huh?
You don't see that on like tests and quizzes?
What?
Do you want us to do that on
Yeah,
like tests?
yeah, a test and quiz. Anytime you give me a Smith chart, number the points so I know the progression you took, how you're getting about. I mean, it helps me grade. I give you a grade that's fair. So that's gamma L right there, right? Now we're now we got to draw this circle. We're in the Y domain because it's going to be hooked in parallel, and this is going to be YL here, and this is something mile markers towards, or wavelengths towards generated there. You can give me the value of this if you want. It's just 1/2 plus say 1.6, but it's not important. This value is important. Can you give that to me?
0.457 lambda.
0.457 lambda.
Yeah.
About that, guys?
These numbers also come from, I did check my answers and I was just, so these are from his answers.
Okay, good. All right, we got that. Now, the question is, he wants the length of the stub minimized,
Yes.
right? So now you can go back to the stub and you think it through. For the stub, since it's open, stub length, ds, in this one. Z of the stub is infinite, right? Y out is 0, correct? It means we're starting at this point, right on the rim. Y'all follow me? Now the first values we encounter are plus j something. If we want to minimize that length line, we have to have a plus j value required for the stub, right?
Yes.
It means the actual line has to have a 1 minus j value. Y'all follow me on that? So where would that be? If you take a look at this, if we move to here, that's going to have a plus j.
But we get minus, so we keep going.
Keep going. And that means you hit over here at the 1 circle. And out, so this is that's point 1, this would be point 2, this would be point 3. Shoot a line down through there and give me the mile marker, the wavelength story.
354.
You agree, class? Just make sure you can see. Can you all see? You see it on yours? You can?
Yeah.
0.354? You got it?
Or wait, that's the wrong one. That's the wrong one. I'm looking at the wrong thing. Sorry. I skipped
That's all right.
to a future step. Wrong line.
Just tell me what it is.
0.32.
0.3 what?
29.
0.329.
That's about what I got.
That's fine. Don't worry about it. All right, so now the total distance we move is from here to here, right?
Yeah.
So now we're going to get the through line distance, and we end up at 0.329 minus 0.4, what is it, 457? That's going to be negative, so I add 0.5 lambda to it. And what's that length?
0.372.
0.372. And what's the value here? 1 minus j what?
About 1.3.
All right. And that value comes from this. It's the trajectory that goes through minus j 1.3, did you say?
Yes.
Minus j 1.3. So now we have to have a positive j, is it 1.3? Positive j 1.3, correct?
Yeah.
So that's going to be about, this is somewhere about here. So that's going to be j 1.3, no, wait, yeah, about there. So what is that distance wavelengths towards generator?
0.171 then.
You guys confirm that?
No, that's .14.
146.
146.
Am I looking at the wrong thing again? Oh, I'm looking at the wrong thing again.
146?
Yeah, my bad.
146? 0.146 length. Is that right?
Mhm.
Now, that would be the length of the stub, right?
Yeah.
Got a question for you after you get done writing this down. This is my personal question. So everything's fine, right? So we use that design, and then some terrorist decides to do this. Comes down here, and he puts an inductor here. An inductor with J 50 ohms. That rat. How do you do, now get the reflection coefficient here, just like the prior one. How would you do it? Now think it through, guys. Isn't that just a transmission line? Right. That's an impedance, right? We could get the normalized impedance, right? Then we could plot it on the Smith chart. You agree with that?
Mhm.
So J50 by 50 is just J. It's 1J, isn't it, class? 1J plotted on the Smith chart. And it'd be on the edge, correct, class?
Yeah.
1J is where? Right here, isn't it?
Yeah.
Right at the top. And then we would move, well, actually, let's do it in the admittance domain. So if 1J, if that's what the impedance is normalized, the admittance is down here, minus J1. Y'all follow me? 1 over that.
Yeah.
South pole. Y'all with me? Now, how far do I have to move? I have to move until I hit this point, which is the stub length. What was the stub length today?
145, 146.
So then I would move from the south pole and I would add that to it. It's going to come up here. It's going to still be J. You all follow me? All right. It's going to have no real value. It's J something. Got me on that? That's y. Hear me, everyone? Now, once you have that value of y, now you come over here. What was the value of y there? It was 1 minus j 1.3, correct? So you would add minus j 1.3 plus the j we ended up with together, and now you would have the normalized admittance at that juncture, right? To get the impedance normalized, you take 1 over that, then you would plot it. If I asked you the reflection coefficient, you would take that down, you know, the magnitude would be down the bottom, and you could measure the angle. Do y'all follow me on that?
Yeah.
So just remember, that isn't, I was like, oh, Dr. Baginski never covered this. Well, I'm just telling you, you've got the theory to do this. Yes, I don't cover every single problem, but the conceptual stuff and the theory behind it, I cover. I try to do real well. Whitworth does too. If I said all of a sudden, let me really be a, this is like the ultimate terrorist. So now I'm supposed to put a capacitor here. Make this J 50 ohms. No, make it minus J 100 ohms. All right? Just think it through. All right? Those two are in parallel, right? That's a transmission line. We're going to do it in the admittance domain. Following? So here, that has got an impedance, normalized impedance of minus J2, right? Normalized admittance of plus J.5, correct?
It'd be J. Z0 is 100, so it'd be J.
Oh, I'm sorry. It would be normalized impedance is just minus J. Normalized admittance is plus J, right? So you would start here, and you would keep moving until you hit this point, correct? You would move through this, whatever that is. The through line is 0.372. You all follow me?
Yeah.
You'd move that far. So whatever the mile marker is up there, which is going to be, so it's 0.125, I think. Up, yeah.
Is that point that you keep referencing, is that just the 1 plus or minus the j term?
Here?
Yeah.
No, that's the length of the stub.
Oh, that's the length? But what is
I'm going from here to here, right?
Yeah.
All right, but here, look. When you normalize that, what do you get?
Oh, it's the length.
Yeah.
Oh.
Is minus J1, right? Then Y, that load would be plus J1, right? Plus J1 is right at the top. Look at your Smith chart.
Okay.
Y'all follow me? But you would do it the same exact way you would solve any problem where they're in parallel using a Smith chart. So then you come back here, you would find the admittance from that thing here, and you would add it to the admittance from this thing here. Then you get the total admittance. Then you get the total normalized admittance. Then you get the total normalized impedance. And then you plot it, and then you get to your reflection. Yeah.
So this is about, like, what you did up there is about what I did. The problem is he says that is wrong.
What is wrong?
Your answer to the problem we just did 2.39.
Wait a second. What is wrong?
He says the answer is wrong. Like
Wait.
the book says the answer to the book give a different answer, and that's why I asked
For
this
what?
question. For the length of the stub.
Okay.
I think he does it backwards.
Yeah, he does it backwards, and I was wondering why he did it backwards, because that wouldn't minimize the length.
He stops at the first point on the one circle. He doesn't go
Yeah,
to the second one.
that's positive, right?
Yes.
We're in the admittance domain, right?
Mhm.
That's a positive admittance. He said open circuit, right?
Yeah.
If this is open circuit, the impedance is infinite, the admittance is 0, right? Admittance is 0 is here, right?
Yeah.
It has to be a plus J for the admittance.
He went all the way down to the minus. Is what I'm.
Well, I mean, oh yeah. I'm sorry, yeah. If this is, so you have to go to here for the first part, not the thing I was talking about. Now you move from here to here, right? We got that, right? And so we went to there, right?
Yes.
Hold it. This is, wait a second, wait. He went from here, say it right, from here to here, right?
Yes.
That's
no.
right.
He went from there to the top one.
To the
To 1 plus J 1.3.
Well, then the stub would have to be where?
It'd go all the way around.
It'd have to, that's
And that wouldn't
long.
minimize it, and so I was wondering why.
Well, he
did it.
made, is this shorter than a petrol wavelength? Is that the stub, is this the right length?
I think so.
Yeah, it is. Yeah.
This minimizes that length. What length did he have for the stub?
0.354.
Now, what he did, is basically go here for the length. I think he did this wrong.
He might have done it because it says based on the previous problem, which is a short, and that's what you do with the short.
All right, if you're using a short, it's different, but I
Yeah.
assumed it was open.
It is, yeah.
Yeah, it's open.
All right, I think he made a mistake. The way I showed you is correct.
Okay.
I'm just telling you, I can't interpret every mistake, but
I was
I
just
probably, he probably, does he say short in the problem?
The 2.38 is a short, and
No.
the 2.39 is an open, but it's using the same stuff from that problem, is what it says.
He assumed it was a short though.
It says repeated for an open-ended though.
Open-ended stub, right?
Yeah.
For an open-ended stub, the admittance, the impedance is infinite.
I mean, you can look at the problem if you want to, though, right
Don't worry
here.
about it. What I've showed you is right. I mean,
Mhm.
there's probably mess-ups in that answer, but that's right the way we did it.
Okay. I was just making sure because my answer, I did what you did, and that conflicted with what you got.
This is, the answers can be wrong, or solutions can be wrong. This is correct. Other question, that's a good question, I'm glad you brought that up. All right, I was gonna go through bounce diagrams today, but I'll just give you your quiz. I've got what? Do I have?
You have until 2:30. Yeah, 20 minutes.
I got 20. Well,
You can go through if you want.
tell you what, I'll give you a reading for the bounce diagrams. Well, I can do, just give me 5 minutes and then take the quiz. It's not tough. But you all have Smith charts and stuff now? I'll just go through this bounce diagram business again. This is the next section. And I'll tell you, this is very, very intuitive.
That's some solutions. You're right. What we did was right.
Yeah, okay.
In the back of the book. So the solution was right. Like,
Okay, yeah, that's what I was thinking, because like, I couldn't like make it work in my head, so I was like, this either has to be wrong or I'm missing something. Yeah, but-
I'm glad you brought up that problem. And I'll tell you, like Dr. Wentworth's book's fairly simple. A lot of times what they'll do is say, use a stub, match it with a stub with a different characteristic impedance and a reactive load, not a shorter open. You guys, it's more and more, I guess, items you have to consider. You can keep on asking complexity. Sometimes they'll say, suppose we want it to go through a wall and has a limit for the lengths, all right? So then you do 2 stubs. It's called double stub tuning. And there are more and more tricks. Then there's wide band tuning for this. This is more advanced stuff, but Dr. Wentworth's book really hits the basics, because this is what, if you're in the field, you really need to know. Okay, this is a bounce diagram. So what do I mean by this? Think of a battery, ye old battery, plus or minus V naught, and you got some impedance, R source. This is like a Dr. Irwin circuits problem. Then you have a switch that closes, say it closes at T equals 0 here. And now I have a transmission line, and it's got a characteristic impedance Z naught. It's got a certain length L, and you assume the velocity on the transmit, phase velocity is C. Sometimes it's C divided by the square root of epsilon relative. I can put that on there, but it's not really. Epsilon relative is usually 1. And then you have a load here. This load is going to be strict real for now. And the load is going to have a value of Z load. And what you want to do is figure out the voltage versus time at any point on this transmission line. So I'm going to, y'all follow me on this? Think about this. Here's what happens. You got V naught here. As soon as you close the switch, there's a plus to minus potential here that will move at the speed of light in that transmission line until it hits here. And then it will reflect. Y'all follow me on this? And then it will hit here and it will reflect. And then it'll hit here and bang, 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 bang. It's called a bounce diagram for good reason. It looks like you're throwing a ball and you got 2 walls very close to each other. Like, has anybody done that with a Super Bowl? Do you know what a Super Bowl is? It's stuff that'll bounce like crazy. We used to go at the YMCA when I was a little kid, and we go in a hallway like that and just whip the thing as hard as we could, and the thing, and try to run through it. You get a lot of bruises. Anyway, so the first thing you calculate is the length of time it takes to get down here. And that length of time is simply the length of the line divided by the velocity, phase velocity. So it's length of the line divided by c times square root of epsilon relative. Usually epsilon relative is simply 1. So this is TL. That's called, I think he calls that the time constant or something. It doesn't matter. Just the time it takes for the wave to move from the source down there, assuming it's moving at the speed of light in the transmission. Next thing you need is reflection coefficient here. And this reflection coefficient will be ZL minus Z0 over ZL plus Z0. Now you guys know that. Then you need the reflection coefficient looking this way, assuming the switch is closed. Y'all follow me? For this one, you have to use Thevenin's theorem on this. So for a Thevenin's theorem, the effective Thevenin resistance, you always short out the circuit. Remember that? The voltage sources become short if they're constant. So it's just RS. So that means the reflection coefficient, I'll call it at the source, sorry, gamma source is equal to RS minus Z0 over RS plus Z0. Now you've got the reflection coefficients, you got everything. You all with me? So the way we do this is, just think about what I'm telling you. Just as that switch closes, you're going to get a certain amount of voltage here. Now, because the switch just closes at the instant, all right, just at the instant it closes, it doesn't know what the load is. Follow me? There's no information down at that end from the load. So the actual impedance it sees is Z0. So the voltage that jumps on here just the instant it's closed is called V prime. And V prime will be simply the source voltage. I call it V0, you can call it Vs. And this is simple voltage division. And then it's just going to be Z0 over Z0 plus RS. Y'all follow me? That's the simple voltage, right? Now that thing, that value of voltage is propagating the speed of light, hits here, then it reflects back and comes back. So what we do, the way we calculate these things, we get a balance diagram like so. This represents the length of the line. And this would be L equals 0 here. This would be L that far away. And this is at any value down the line, call it Z. On this axis, it's time. And you always go down to TL, 2TL, and I'll show you why, 3TL, 4TL, and we can keep going, but I'm going to show you how this works. Y'all with me? Now, T equals 0, the switch closes. This transient's on the line, it's moving down. And at TL, it's going to hit there. So what you do is just draw a straight line till you hit TL on this side. This indicates the trajectory or the path that the voltage would take in space-time. And by that I mean, if you wanted to know where the voltage pulse was or how long it took to get there, and you're, say, halfway down the line, you would go from here downward, there's nothing, 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 you hit here, there's V prime. So it would take that long. If it was halfway down, it would take TL over 2 to get there. Y'all with me? So it hits here, this is all V prime, and then it comes back this way, and it's going to have V prime times the reflection coefficient below the value. Y'all with me? Keep drawing that back to here. Hits here, how many can see this? This is going to be V prime gamma L. Now it's going to come this way, and it's going to be V prime gamma L gamma source. Keeps coming down, hits here, at, it should be 3, right? Let's see. Yeah, this would be 3, and so forth, all right? So suppose you want to sketch the voltage at the load. Just watch this. If I want versus time voltage at the load, it's 0 until it hits TL. Y'all with me? It takes that long to get there. With me? It's 0. at TL, now look, at this point, it's a superposition of the incoming and outgoing. Y'all follow me on that? So now it goes to a value here that's going to be 1 plus the reflection coefficient of the load times V prime. And it's going to stay there for how long? What's the difference? 2 time constants. Y'all see that? Everybody? Now, when it hits here, that's going to be at 3 TL. Now, this is still there. Now you add this value. What's that going to be? It's going to be V prime gamma L gamma S times gamma S, and also V prime gamma L gamma S. V prime gamma L gamma S times gamma L, or V prime gamma L squared gamma S plus, well, here, I'll just write it down. So now it's going to go, it has the old value, V prime, it's going to have 1 plus gamma L plus, then it's going to be gamma L squared gamma S. Or, I'm sorry, gamma L gamma S, my bad. Gamma S plus gamma L squared gamma S. And what I've really done, yeah, that's right. You can see that I've just added this, I superimposed this incoming plus this outgoing at that point, and you keep going. And when it's going to asymptotically approach them. I got to give you a quiz now. We're going to cover this. I'm going to give you some reading. I'll give you some homework for Monday. Please do. But I'm going to give you your quiz. Y'all with me on this? Okay. Take everything off your desk. Do me a favor. Can you hop to that row? And then you hop to this row.